Well, nowhere to go but up from here. Um, Anybody have any questions from the stuff we talked about last time? Okay, so last time we defined position as a function of time, talked about what that meant. You need to choose three things before you can relate a physical object's motion to a position versus time graph or a position function. Those three things are zero position, a positive direction, and a zero time. And once you have the function position versus time, position is a function of time, we defined the instantaneous velocity also as a function of time. And v of t is just equal to the time derivative of the position, so p dot or d dt of the position function. Okay. And can position be any sign, or does it have to be positive? Any sign, and the sign tells you which side of the zero it's located on. Can velocity be positive or negative? And what does its sign tell you? Which direction it's moving, that's right. Okay, so now we're going to define the instantaneous acceleration. You can think of this intuitively as how quickly the velocity is changing at a given instant. And the definition of acceleration as a function of time is the time derivative of the velocity. And since velocity is the time derivative of position, you can also think of this as p double dot of t, or the second time derivative of the position function. If the acceleration is positive, if you're thinking about a position versus time graph, okay, so if acceleration is the second time derivative of position, what would be the characteristic of positive acceleration on a position versus time graph? Yep, very good. So position versus time graph is concave up. And if A is negative, it's concave down. Okay, so now let's think about how to know based on the acceleration at an instant whether an object is speeding up or slowing down. Okay, so remember, an object can be moving in either direction, positive or negative, right? Its velocity can be positive or negative. So how do we know if the object is speeding up or slowing down? Um, well, your first thought might be that if an object's speeding up, the acceleration has to be positive. If it's slowing down, the acceleration has to be negative. But there's a little bit more of a complicated relationship than that. So if the velocity and acceleration have the same sign, the object is speeding up. And if velocity and acceleration have opposite signs, then the object's slowing down. So if an object's moving in the positive direction, its velocity is positive. Its acceleration, if it's positive, then the object's speeding up in the positive direction. If the object's velocity is positive and its acceleration is negative, then it's moving in the positive direction and slowing down, you know. If its velocity is negative and its acceleration is negative, then it's moving in the negative direction and speeding up and blah, blah, blah. Okay, so let's say we have a position versus time graph that looks like this. And I'm going to call this point A, B, C, D, E. So first, over what intervals or interval is the object moving in the positive direction? Same question now, but negative direction. Over what intervals is the acceleration positive? The acceleration negative. When is the object speeding up? And when is the object slowing down? Okay, so let's okay, so the graph looked like this. So the velocity, the sign of the velocity just has to do with whether the slope is positive or negative. So the velocity was positive on the whole first half of this graph. If this is A, B, C, E. So the velocity was positive, A to C. Velocity was negative, C to E. The sign of the acceleration has to do with the concavity. So the acceleration was positive when it's concave up. So A to B and D to E. The acceleration is negative when it's concave down, so B to D. And for speeding up and slowing down, I think the easiest way to think about that is on each one of these intervals, just think about what's the sign of the velocity. Here it's positive. And what's the sign of the acceleration? Here it's positive. And so since those have the same sign, that region has to be speeding up. Here the velocity is positive, the acceleration is negative, so that has to be slowing down. Here the velocity is negative and acceleration is negative. Same sign, so that's speeding up. And here the velocity is negative, acceleration is positive, so that's slowing down. So it's speeding up A to B and C to D, and slowing down B to C and D to E. Any questions about that? It seemed like everyone understood that pretty well. So now this second question, what does a position versus time graph look like for first constant position, which is equivalent to zero velocity? And second, change that to part B. Let's actually do a part A that says position equals 0. Well, I already asked it. All right, so velocity equals 0, and then the third one is for velocity constant, which is the equivalent of acceleration equals 0. So what's required for those? Position equals 0 can only look like one thing. You know, that's if here's your position versus time graph. It has the graph just has to be have a value of p equals 0 the whole way. Notice that, remember I said we're not ever going to deal with negative times, so the graph starts at time equals 0 and only goes in the positive direction. Okay, the second one, what does it take for velocity to be equal to 0? It's a straight line with no slope. That's right. So it could be this, or this, or this, or the one we had before, any of those, but it can't have any slope. And then what does it take for the acceleration to be 0 or for the velocity to be constant? It's a line, yep. So it could be this, or this, or this, or this, but it can't have any curvature. So notice that if the position versus time graph has curvature, then the acceleration has to be non-zero. Just looking at a position versus time graph, you can tell if there's acceleration or not. If it's a straight line, there's not. Yep. No, you can also have, so those are the three things that can happen if there's no acceleration, I guess. But what you see with all of these is the position versus time graph is a straight line, because in all the cases, you know, there's different requirements for what the straight line does for those different cases. But if there's no acceleration, it has to be a straight line. So if you ever see a graph that's curving and stuff, you know that there has to be non-zero acceleration. Acceleration is the only thing that can make the graph, you know, have curvature. Okay, so now let's talk about moving between position, velocity, and acceleration. So first, if you're going in the direction of P to V, or V to A, or P to A, if you're going in that direction, all you're doing is taking derivatives with respect to time. So knowing the starting function is enough. Okay, so if you know that position versus time is equal to cosine t, then that's enough information to know the velocity. You just take the time derivative. It's different if you're going in the other direction. So if you're going from A to V, or V to P, or A to P, knowing a function isn't enough. And why is that? That's right, because you're integrating. And so you need to know those constants of integration. So you need a starting function and a constant of integration for each step. Okay, so for example, let's say that you start with a function of the instantaneous velocity, v of t is equal to 3t squared. Let's say first, we want to figure out acceleration as a function of time. Is that enough information? Yes. And then second, let's say we want to figure out position as a function of time. Do we have enough information? Nope. We also have to be given something like at time equals 0, position is equal to 2 meters. Okay, so for part A, the acceleration as a function of time is the time derivative of that, so 6t. For part B, the position is, so p of t is the integral of 3t squared dt. And so that's equal to t cubed plus c. Yes. What's the difference between those two? Okay. You don't have to write it if you don't want. Okay, so now how do we figure out what that constant c is? That's right. So now we'll say, so if p is equal to t cubed plus c, then 2 is equal to 0 cubed plus c, and that tells us that c is equal to 2. Have you done that kind of stuff before? Okay, good. So then position as a function of time is equal to t cubed plus 2. So there's your acceleration, and there's your position. Okay, so now let's say, I don't think any of these ever change, so is the object in positive or negative, position, positive or negative direction, moving in the positive or negative direction. And is it speeding up or slowing down? Okay, so to figure out if it's in the positive or negative position, you look at the position versus time graph. That's this one. Is that ever negative? That's right. That's right. Time can't be negative, so this is always positive. The velocity function with, well, it doesn't matter in this case. Can that ever be negative? Nope. So it's always moving in the positive direction. And is the acceleration positive or negative? positive the whole time. And so is it speeding up or slowing down? Speeding up, the acceleration is always positive, velocity is always positive, so it has to be speeding up. By the way, I didn't say this when I was talking about speeding up or slowing down, but how do you know whether it's speeding up or slowing down if the velocity is 0? Well, it's actually always speeding up because you can't get any, like stopped is as slow as you can get. So if you're stopped and you have a negative acceleration, you're speeding up and starting to move in the negative direction. Okay? You can't slow down from stopped. What if you could? That would be so trippy. Yeah. The direction of the dimension of slowness. Okay, so now, well, why don't you do this one on the board? Let's say you know position is a function of time is equal to cosine of 2t. So figure out velocity is a function of time. Acceleration is a function of time. Figure out when the object moves in the negative direction. And figure out when it's slowing down. Yes?
So for the questions up earlier, you based like is object going in positive or negative direction? That's based on velocity, right?
That's right.
So the velocity is a squared function.
Right.
So it opens up.
That's right.
And
Yep. But we don't care, but even if we did care in this case, it would always be positive. But for us, we only deal with positive time, so we don't care what happens when time is negative.
So like if it was a negative.
Right. Yes, exactly. Yep. Okay. Go back up to the board and see if you can think through this one. Okay, so the first part is just taking derivatives. So what was the function? Cosine 2t. So you have to use the chain rule. Velocity is equal to negative 2 sine 2t, and then use the chain rule again. Acceleration is equal to negative 4 cosine 2t. And then for C and D, there were sort of two ways people did it, either graphing it out and using the way we were sort of thinking about the last couple examples, or trying to do it based on the function. The people who tried to do it by thinking about the function, I think, had a way harder job to do. The easier way to do it is just, so graph the position versus time function. It looks like this. And the argument of the position function was 2t, so this is going to be going with like twice the frequency. So instead of pi over 2, this would be pi over 4. Oh, I see why. Yeah, right. You were asking me whether it was going to pi or to 2 pi. Yeah, right. I was thinking of pi. You were right, I was. And then this is pi over 2. This is 3 pi over 4 and pi. And so now you can think about it the same way you did with the other functions. From 0 to pi over 4, is this moving in the positive or negative direction? Yep, so velocity is negative. Is the acceleration positive or negative? Yep. Then on the second interval, is velocity positive or negative? Velocity is negative, but acceleration is positive. Here, velocity is positive, acceleration is positive. And then velocity is positive, acceleration is negative. So if we're looking for the intervals, well, so when it's moving in the negative direction, that's all the way from t equals 0 to t equals pi over 2. And for when it's slowing down, that's pi over 4 to pi over 2, and then 3 pi over 4 to pi. And then since I said, oh, the t equals 2 pi by accident, then you have to do it again, but I'm not doing that. Any questions about that? Okay, let's take a 10-minute break, and we'll start again at 10 to 9. Okay, here we go. So in the examples that we've been doing, acceleration varies, right? I mean, if you look at that acceleration function, it's different at every time. But there are a lot of important cases where acceleration is constant. And so we're going to, pay sort of special attention to those cases. So constant acceleration. So we're going to assume that acceleration is the constant lowercase a. And we're going to say that at time equals 0, velocity is equal to the constant v sub 0, and position is equal to the position p sub 0. And we're going to, just from the fact that acceleration is a, and given these constants of integration, we're going to derive functions for the velocity and the position. Okay, so we'll start with the acceleration as a function of time is equal to this constant a. Then velocity as a function of time is the integral of a dt, which is at plus a constant. Well, we know that when time is equal to 0, v is equal to v sub 0. So to use that boundary condition, we'll say v sub 0 is equal to a times 0 plus c. And that tells us that that constant c is equal to v sub 0. Who's with me on that? Okay. And so we have this function. So this is the acceleration function that we're starting with. The velocity function is equal to, I'm going to reorder it because people usually do, but now we know that it's equal to v sub 0 plus at. Acceleration is a everywhere because this is constant acceleration. Oh, I see. This is not a function. These two are multiplied together because when we took that integral, we got a times t. And so now what I'm doing is, okay. So now we're just substituting in at time equals 0. We know this is velocity. We know this is time, and we're calculating c. And now we'll do the same thing to get the position. So position is a function of time, is the integral of the quantity v0 plus at dt. And so that's equal to v sub 0 times t plus 1/2 at squared plus a constant of integration. And we know that when time is equal to 0, we're saying that p is equal to p sub 0. So p sub 0 is equal to v sub 0 times 0 plus 1/2 times a times 0 squared plus c. So again, c is equal to p sub 0. And so p is a function of time is equal to p sub 0 plus v sub 0 times time plus 1/2 a t squared. Yeah, sure. I sort of thought of it as like we're doing two separate problems, but I think might as well do this, yeah. Those are two separate C's. So once we calculated velocity as a function of time, then we know position is the integral with respect to time of velocity. So we took what we found for velocity, integrated it again, used that second constant of integration, and came up with a function for position. Okay, so what are these?
Does like p sub 0 mean it's the 0th interval?
P sub 0? No, that's just the name of a constant that represents the position when time is equal to 0. So that's what P0 and V0 are, both just the position and velocity at time equals 0. Okay, so these equations only hold when acceleration is constant. And so that's specific cases. We couldn't have used these equations to solve the problems you did up on the board because those had varying accelerations. But and there's one more equation that we're going to use. So we'll derive one equation without t appearing. And we'll do that by, so we know that velocity is a function of time is equal to v sub 0 plus at. And so I'll rearrange that and get t is equal to the velocity function minus the velocity when time is equal to 0 divided by a. And then we'll substitute that into the position function. So the position as a function of time is equal to p sub 0 plus v sub 0 times time, but now we're going to substitute in this thing. Plus 1/2 times acceleration times that thing squared. Which is v squared minus 2v0 times v plus v0 squared over a squared. So p of t is equal to p sub 0 plus v0 times v minus v0 squared all over a. Plus, I'll write this as v squared as a function of time over 2 minus v0 v plus v0 squared over 2 all over a. Why would I write it like that? It's sort of an ugly way to write it, but now you can see some stuff that cancels because these have the same denominator. So this cancels with this. Well, I'm deriving the equation that you're going to need to use. I think as far as like what you should understand about this derivation, I think yeah you should remember sort of, you don't have to be able to do every step smoothly or whatever, but you should know what I started with and what the process was, because it'll help you understand well, yeah, just where we got these relationships, when you can use them. This second one after sub into position. So we came up with that position function that says for constant acceleration, position is equal to p sub 0 plus v0 t plus 1/2 at squared, right? And we came up with that velocity based on our velocity function. We express t this way. So now I'm just expressing this, I'm just using this expression for t that we got from the velocity function and plugging it into the position function. I'm combining these two to get rid of the explicit dependence on t. Any other questions on this? And yeah, it makes sense, you know, and it's just like algebra and stuff. Like, any other questions? So now, position as a function of time is equal to P0 plus, I can add all these terms because they have the same denominator, right? So I canceled these two. V0 squared over 2 minus V0 squared is minus V0 squared over 2. And so we have, I can write this as V squared over 2 minus V0 squared over 2 all over A. And so I'll rewrite this as P is equal to P sub 0 plus V squared minus V0 squared all over 2A. And then the final form that people use, subtract P sub 0 from both sides and multiply both sides by 2A, and you get 2A times the quantity P, I guess this should be a bracket, P minus P0 is equal to V squared minus V0 squared. And people don't usually, yeah. People don't usually keep writing the P's and P and V as functions of time. So I'm just going to change that to P and V. That's what it means. We're talking about P and V at a specific instant. Yep.
So where would this come into play? Would there be a little confused.
No, you could always do the derivatives and integrals and stuff. This will just save you some time because constant acceleration comes up so much. Like basically using the derivatives and integrals would just mean rederiving this every time, you know. Yeah, for constant acceleration, they always work. Yep. So the last form of this is 2A times the quantity P minus P0 is equal to V squared minus V0 squared. So that's the last one of these important equations. And the most important case of constant acceleration is free fall they're different.
The constant acceleration would still be a curve.
Right.
And no acceleration.
That's right. That's right. That's right. So free fall and projectile motion. So if the acceleration is always equal to 40, that's constant acceleration, you know? So free fall and projectile motion are when the only significant force on an object is from gravity. Okay, so most of the problems we're going to be doing are free fall, projectile motion. Yep. It's not, so that T that I'm pulling around in this case, the last case it was multiplied. In this case, it's just saying, reminding you that those are functions. So this is just a shorthand. P and V are just shorthands for those as functions of time.
So those are functions.
They're functions of time at some specific time. Right? So this is saying this V and this P have to be at the same instant. And you know, some of that stuff I think it'll be pretty clear once we've done a couple of problems. But yeah, so in that other case, somebody asked me about like, oh, why is that a function? Like, no, that wasn't a function. Those two are multiplied. And this was like, well, how can you do that if they're multiplied? They're not. This is a function. That is a little confusing. But again, like, I guess that's why you go through the derivation, is so you can make sense out of what all this stuff means, because you sort of have an understanding of where it came from. Okay, so the most important case of constant acceleration is for problems in free fall and projectile motion. And all it takes for something to be in free fall or projectile motion, and those are synonyms, is that there's no other significant force acting besides gravity. That means that, so air resistance is always acting on things, but this is saying you can use these equations in the case where air resistance is small. And we have to talk a little bit about when air resistance is small and stuff like that. But I want to show you a movie that demonstrates this, because, you know, so Galileo was the first person who did experiments to show that the way the motion of objects in free fall did not depend on their mass. Before that, people had thought that if you dropped a heavier thing and a lighter thing, the heavier thing fell faster. Sometimes that's true, but when it's true, it's only due to the fact that there's more air resistance on the lighter thing. Well, no, not more air resistance, but the air resistance has more effect because there's less gravity. Air resistance has a bigger effect on the lighter thing. Okay. So, and so he, in his specific experiments, figured out that the mass didn't affect how fast things fall. And ever since Galileo and then Newton came up with all these equations for it, we've understood that no matter what two things you have, you know, like a piece of tissue paper and a horse, okay, if you drop them at the same time, right, but what we've understood is that if there were no air resistance somehow, then they would hit the ground at the same time. Yes. Or, okay, yes. How about a big rock and a tissue paper? Then no one gets hurt. Okay. No, they're not. Hey, wait a second. No, they aren't. Yeah. Okay, so we've understood that, but the chances to do an experiment with no air resistance are pretty limited. But here's a really cool video of a gigantic room that they use for rocket experiments, where they can actually suck all the air out of the room. And then, so normally they haven't built this big expensive things for dropping objects. But in this video, they take a bowling ball and a feather, pump all the air out of the room. Yes, it's a gigantic vacuum chamber, and you can actually see the feather and the bowling ball fall exactly the same if there's no air resistance. Really cool. Here we go. Yeah, I want you to learn that too. Not today. We'll watch that later.
Growing up, I was always the littlest guy on my team. Even now, I think I still am.
Oh no, that's the punchline. We didn't want that one. We want the little bit wider view of this. Okay.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems.
So, first, has the air been pumped out yet? How do you know? Yes, because he's alive. That's correct. That's right. You can see an open door. That's true. Those are all good reasons. Yes. Oh, that's true. The sound. I didn't think about that. Very good. Yeah. That's not very much.
And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Okay, that's what we're used to.
Now, in this case, the feathers fell.
But he's still alive, so we know.
Slower rate than the bowling ball because of air resistance.
So, watch what happens as they start pumping the air out. Slowly, you're going to see Brian Cox start to explode from the pressure inside his body. Okay. Not really. Actually, they have him leave first.
So, in order to see the true nature of gravity, we have to remove the air.
He sounds like a villain in a James Bond movie.
It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 managed, 10% over. Station 1.
Yeah, they need a better pipe there, I think.
CB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4, 2, 1. Release.
Is this with all the air out?
Look at how cool that is. Like, The feather isn't fluttering or anything like that because there's nothing to make that happen. And watch, like, when the feather hits the ground and, like, bounces, like, violently.
They came down exactly the same. Wow.
Look.
How they hit right there.
Exactly.
Back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that. That's just brilliant.
Isaac Newton would say that the ball and the feather fall because the
So, right, that's right. Or they might have pumped all the air out of his body too, and then he also wouldn't explode. So, in cases where where air resistance has a limited effect on the motion, the acceleration of every object is the same. So remember, this is where we inserted the Brian Cox video.
Yeah, that's what I was saying. It was a big rock and a small rock.
Yeah, different. Yeah, so we'll talk about that stuff a little bit. It's funny. So it's not exactly that feathers necessarily have that much more air resistance. The real issue, because imagine dropping a bowling ball and a beach ball that's the same size. They would have like basically the same air resistance, but the bowling ball would hit the ground way sooner. What really matters isn't just the air resistance, it's the ratio of the force of air resistance to the force of gravity. And gravity is, like if you weigh a beach ball, that's measuring the force of gravity. It's a lot less than the bowling ball. So the same air resistance has a much bigger effect on something with a smaller mass. Feather and bowling ball.
The reason they fall at the same rate is because there's less force acting on the feather, but it's also lighter.
Yes,
So
that's right. Yep. So if
Do they fall at the same rate only because they're both so relatively small that it doesn't affect anything? Like if you got a super massive, ridiculously massive bowling ball, wouldn't the super massive thing fall faster?
No.
or a tiny bit, right? Because of gravity. Like, isn't there a tiny bit more force acting on the massive thing?
If you got something massive enough, so if you got something massive enough that its gravity affected the motion of the Earth, then it wouldn't really be. I mean, then the Earth would be accelerating a little bit towards the object, and then you'd have to stick it. But no, as far as just like it falling faster, no, it would be the same. So for now, we just kind of have to accept that they do, but when we start talking about forces and stuff, we'll understand why that is. Okay, so the bottom line for freefall is if the effect of air resistance on an object is negligible, then an object in freefall, and again, freefall I use as a synonym to projectile motion. So something launched out of a cannon is in freefall. All freefall means is that the only force acting on it at that instant is gravity. Then an object in freefall accelerates down with a magnitude g, lowercase g, and that g is equal to 9.81 meters per second squared. That's sort of an average at like sea level on Earth. Yep. Right. Same thing with helicopters. I mean, a helicopter, the only thing holding a helicopter up in the air is the interaction between the blades and the air. That's right. Yeah. So like when people get stranded on like high Himalayan mountains and stuff, mountain climbers, you're just like, why don't you just fly a helicopter up and get them? Helicopters don't fly like much higher than like a helicopter can barely get up to the base camp of like the starting point of Mount Everest because the altitude, the air has so little density. And so if you're up on the mountain, there's nothing anyone can do. So if they did that experiment with a feather and a bowling ball and a helicopter in that room, the guy would be driving the helicopter with the rotors going, and it would be falling right down with the bowling ball. Yeah, you're so sensitive about the killing things for these experiments. Yeah, exactly. It probably depends on the guy. Yeah, right. So let's do one quick example problem, and then we'll stop for the day. So let's say you want to figure out how high a bridge is. You're standing on a bridge. You have like something that isn't going to be affected by air resistance too much, like a rock or something. And you want to figure out how high the bridge is without having to lower down a tape measure or something. So the way you could do it is drop the rock, if you have a stopwatch or something. Drop the rock, see how long it takes to hit the water. Be sure that no boats are going under. And like the guy's like, the helicopter driver's like, oh, thank God, I finally recovered from the helicopter. Ah! Yeah. So let's say a rock takes 0.30 seconds to hit the water when dropped from a bridge. I think it needs to take longer than that. Let's say 0.6. How high is the bridge? Well, we can use the equation that says position is equal to the position when time is equal to 0, plus the velocity when time is equal to 0 times the time, plus 1/2 times the acceleration times the time squared. We have to think about our choices of position equals 0, positive direction. So let's say position equals 0 is on the water, at the surface of the water. Positive direction is up. And our time equals 0 is going to be when it's dropped. I don't know.
Maybe.
Could be. Who knows? Maybe that helicopter driver could tell us if we hadn't wasted him on that experiment. Such a waste. Okay, so do we know the position at time equals 0? I'm sorry, do we know the position at 0.6 seconds? Yes, that's 0, right? Do we know the position at time equals 0? No, that's what we're trying to find. Do we know the velocity at the instant it's dropped? We do. If it's dropped, then it's 0 at the instant it's released. Terminal velocity is not something that we deal with in problems like this, because terminal velocity is at the instant when the force of gravity is exactly balanced by the air resistance. So that's a very significant air resistance effect. You know, so air resistance is only when you're dealing with it. Sorry, terminal velocity only happens when you're dealing with air resistance, and we're not here. Okay, so the velocity is 0 at time equals 0. The acceleration magnitude is 9.81 meters per second squared. Is that positive or negative? Well, our positive direction is up. The acceleration is down, so it's negative. And then the time is 0.6, and that's squared. So we have 0 is equal to P0 plus 4.905 times 0.36 negative. And so 0.6 seconds to hit the water, yeah. And can someone multiply that? I don't have a calculator.
It's
1.27. This second term was negative, this was positive, and then we're solving for P sub 0. So 1.275 meters, that's a pretty low bridge. But, yeah, right. I suppose it's possible. Oh. Okay. We'll do a lot of problems like that, and we'll get into some rules for like starting velocities and things, but that's the basic idea of using those constant acceleration equations. Yes? Question? Any other questions? Okay, see you Friday. So remember that Friday is going to start with like a 5 or 10 minute quiz on stuff that I've said in class. Okay? There was nothing on, I don't think I gave you anything to do. It was just a reading assignment. But Oh, did I assign problems from it? It's just on D2L. Okay, so I just sort of put those all up there. That's all the problems for the semester. I'll tell you on D2L in the notifications when you should do each problem. What? No, it's in the other. It's on the other side of the building. I'm sure Meredith will bring you there.
The markers?
Oh, you can just leave them up there. Thanks.
No, if I should throw them